Thank you. And I want to thank the organizers, Stephanie and Sevilla, for inviting me here to this beautiful place with very interesting talks. My talk today actually goes back to where I started in 2009 when I started as a postdoc. My PhD was in pure maths and singularities, but then I moved to a computer science department, and my mentor, Mads Nielsen, asked me the following question: how can you do statistics or machine learning on data when your data has additional structure, like a tree structure? And our running example was airway trees from the human lungs. They do not have the same number of branches from person to person. They do not have the same topological structure from person to person. There are general patterns that are similar, and you can see that with your eyes. But there are also both structural and shape-wise variation in these trees. So the sort of motivating questions were for instance, how does the average of a set of airway trees look like? How does the tree topology and the branch geometry vary? How do they vary together? How can you combine them in one framework? Does the structure and geometry differ between, for instance, people with a disease and people who don't have it? And can we find and visualize these differences? Now, often if I talk to machine learners, for instance, they say, well, why don't you just use a kernel? Or these days they say, why don't you just use a neural network? And what kernels or neural networks do is they learn discriminative embeddings of your data into some linear space, and then they use classification algorithms in those linear spaces. And quite frankly, in my experience, if all you want to do is predict classes from trees, or continuous variables from trees, you probably should do that. Because those tools that exist, they work very well. However, if you want to predict trees, it's a different story. Because once you've embedded your data into some space that is good for whatever task you want to do, well, you don't have the trees anymore. Now you have a bunch of points in a linear space. So if you want to go back and say, well, what does a typical tree look like? How do the trees vary between different extremes, such as health and disease? Or if you want to predict trees from other variables, for instance, if you want to make personalized models, well, you can no longer do that after you've stuck your trees into some other space. So what you really gain from studying trees within a domain of trees is interpretability. You can go back and understand what was it that caused something to happen in your model. And in medical imaging, which is what we do in our group, that's very important. So when we set out, our plan was to try to build a geodesic metric space of trees. We didn't know if it would have any other structure, but at least we wanted it to have geodesics, so that we could interpolate between trees. If you look at what's happening on the right-hand side of this tree, you can see the topological structure is gradually changing as you move to the tree. And this is the sort of properties that we wanted to have, that you could continuously deform not just the branch shapes, but also the topological structure. And to talk about continuous deformation of something discrete like topological structure, well, it might sound wrong, but on some level, that is what we are doing. And then, once we had geodesics, and if we're lucky, some geometry, we can use this to define and compute statistical properties. Now, before we try to define something like this, let's just think about what the consequences would be of having such a space where you can interpolate in this way. Now, I can start out with many different types of trees like this and start contracting some of the internal branches and end up with trees that come from different topologies, but at the end have the same topology. So this sort of indicates that, well, as long as I have trees within the same topology, it's fairly easy to interpolate between them. They live in their own little space. And you can glue these spaces together along subspaces where you find these contracted trees. Now, if you do that, you're almost bound to get spaces, or you are bound to get spaces, where you have different subspaces coming together, and you're going to have self-intersections like what you see here. So this is not a consequence of a particular definition. This is a consequence of the goal of having such continuous deformations between the trees. You will have singularities and you will have self-intersections. You will also have sort of conical bubble-like structures. So if you look at different ways that you could get from this tree here to this tree here, well, you could either contract the branch in the middle and grow something back out like this, or you could contract the side branches and grow new side branches out. These are two different paths that take you from here to here. So if you reverse one of them, you get a loop in your tree space. And the only way that you can contract that loop to a single point, given the properties that we said we wanted from our deformations, the only way you can do that is by contracting all the branches that are involved in these geodesics. So in other words, contracting it to a single point. So just from asking for these types of properties in your interpolations between trees, you're going to have tree spaces with singularities, and you're going to have self-intersections, and you're going to have conical types of singularities. So just to specify a little bit, we're going to consider attributed trees. So they will represent, perhaps in my case, something, a tree-like shape. They will have some underlying topology, and I will attach vector-valued information to the branches. So they could be edge lengths, they could be edge shapes. In principle, it doesn't have to be vector-valued, but everything I do will be. Now, there is actually, in the literature, a way of defining distances between trees that satisfies all of these properties. It's called tree-edit distance. I think it was defined. There are some works from the 70s for sure, it might have been even earlier. And it defines a distance between two trees as the minimal total cost of deforming one tree into the other using three basic types of edit operations, which are to remove an edge, like I just removed this middle edge to get this tree. You can add an edge, so now I've added this tree in the middle, or you can change the attributes of your edges, or if they are shapes, you can deform them, which is what's happening down here. Now, assuming that your edge costs are metric, this gives you a metric out. And assuming that the edge costs are geodesic, give a geodesic metric on the edge spaces, or edge attribute spaces, you also get the geodesic space out. So the tree spaces with the edit distance is a geodesic space, but it has some properties that we maybe don't like so much. So first of all, almost all of the geodesics between two trees are going to be non-unique. So look at this very simple example, a tree with one single branch here and another one with a single branch there. Now you could get from here to there by removing your side branch and growing the other one out, or you could grow the other one out first and then remove. Or if you have continuous metrics on your branch attributes, you could do a little bit at a time, remove a bit, add a bit, remove a bit, add a bit. And because of the way the metric is defined, these would all give you geodesics. So you would have infinitely many geodesics between those two, which means if you're considering the average of those two trees, well, you can have infinitely many averages. Now you might say, I want more than two trees, so maybe it's not so bad. But if you think of it in terms of curvature, this means that the curvature of the space is going to be unbounded everywhere, because if you have bounded curvature, then for sufficiently closed trees, you have unique geodesics. So if you don't have unique geodesics, your curvature is unbounded. This just means a lot of the tools that we use in manifold statistics are not going to apply in this case. Of course, you could go out and develop new ones, but that's not straightforward. So what people have done instead is to say, well, let me just prefer a certain type of geodesics. Let me prefer simple ones where first I remove stuff and then I add stuff. I don't know if you can see this, it's maybe not so clear, but these are skeleta of shapes. These are some hand shapes. And in some of the hands, you can only see 4 fingers. So in the mean figure that you get out, you also only have 4 fingers. And here are some skeleta of men, where at least, I think exactly one of the guys has only 1 leg. And then the mean guy also has 1 leg. So you see, this really impacts the results that you get out. So instead, we define a different distance, which will turn out to be related, but it is different. So to be a little bit more formal, we parameterize our trees, again, as I've sketched before, as consisting of a combinatorial structure. This is going to be represented by an infinite rooted ordered binary tree, which will describe the topology of your tree, or the combinatorics. And then on all the edges, we'll have edge attributes represented by an x belonging to the direct sum of all the edge shape spaces over the edges. So, and because it's a direct sum, you'll always have only finitely many non-zero edges. So in other words, the same figure as before, this is your tree topology, and these are the attributes attached to the edges. Now, we're allowing our edges to be contracted, which means that although I assume that my combinatorial structure would be binary, I can actually represent higher order vertices by having zero edges. So this dotted line here represents an edge with a zero attribute, which means it's contracted in the tree. And you can also represent trees of different sizes by having zero attributes on your leaves, and this is why it's fine to have an infinite binary tree parameterizing all your trees. So if you fix your infinite ordered rooted binary tree that's going to parameterize all your trees, this direct sum of over edge attribute spaces now gives you what you can call a pre-tree space. I used to call this a pre-shape space, but I don't dare to do so anymore because there are a lot of things I'm not factoring out. So let's call it a pre-tree space. Now, this parameterizes all the possible trees you could have. But it is not your final tree space because, for one thing, many trees have more than one representation, which is not practical. So here, if you imagine contracting all the dotted line edges, you end up something looking like this, and the same thing if you go from here up there. So these trees have more than one representation. This in particular means that some of the natural deformations between trees that you could imagine are not represented as paths in the tree's pre-tree space. So if I want this deformation that we've already seen today, well, it's easy to go from this side to this side. I just contract an edge. And it's easy to go from this side to this side, but these two trees, they're now different points in the pre-tree space. So in order to get the sort of space that I want, I'm going to have to do something. And what you do is you define an equivalence where you define different representations of the trees to be equivalent. And if you want to be formal about that, well, you'd say, well, I have my tree representation. I contract all the zero attributed edges in both my trees. If I now have a tree isomorphism from one to the other that takes attributes in one to identical attributes in the other, then they represent the same tree. And you can formalize this for ordered trees or unordered trees, depending on what you prefer. Now this gives you a space of ordered or unordered trees as a quotient with respect to the equivalence. And this is going to be an infinite dimensional space, and it's going to be essentially a folded vector space. So to see what I mean by that, let's look at an example where I restrict myself to trees that have at most 2 branches and generation 1. So not very interesting trees, but sufficiently simple that I can draw what's going on. And let's in this case consider ordered trees. So now the planar embedding of the tree is part of the definition. So now in this case, if I look inside, well, if I represent them with just real numbers as edge attributes, now inside the orthons, I find unique representations of trees because of the order. So the only place where I find multiple representations of the same trees are along the axes where I find represented trees that only have a single branch. In this case, it doesn't matter if it's the first leg or if it's the second leg that's been contracted. So I really find the same tree shapes along these axes. So when I glue these together and take the quotient, I end up with something looking a bit like this. So I'll have like a conical So what I'm doing is I'm really gluing the x and the y axes together, so I get these conical structures out. That represents the folding that you see. And this really is, you can really think of it as a folded vector space. And I can endow this quotient with the quotient pseudometric inherited from the Euclidean space. And I will use this as my tree space metric. So in principle, I could use a different attribute space for my edges, and I could use a shape space, or I could use something else that I like and descend that. And a lot of what I will say carries through, but some of the points I will get to later on curvature might not. So the first observation that we can make here is that now the obvious thing to do here would be to just take the Euclidean norm in here. But you could also take an L1 combination of the edge shape norms. If you do that, you retrieve the tree edit distance metric. So in fact, this interpretation as a folded vector space, it also holds for the tree edit distance metric. It's just not the way we're used to thinking about it, because it's defined algorithmically. Moreover, if you fiddle around a little bit with the topology, you can easily show this is a geodesic metric space. So it's not just a pseudometric, it's a real metric, and it is a geodesic metric. Now, unfortunately, in these tree spaces, because you have these conical structures, you are not going to have unique geodesics everywhere. In fact, but what we can show is that if you pick a generic starting point, and then you pick another generic endpoint, there will be a unique geodesic joining them. So we do have some uniqueness properties. So from the first part here, you can see in this general tree space, your curvature will not be bounded, but not in general, but if you pick a random point, you will have bounded curvature. Moreover, and this was what killed the general formulation, is if you look at the unordered trees, then your geodesic metric is NP complete to compute. So that's bad news. But nevertheless, it's a general formulation that covers, or that has relations to many of the things we're used to doing. And also, the same NP completeness for unordered trees holds also for the tree edit distance. So another tree space that's actually older than the one I worked with, I think it originates from 2001 in a paper from Bilera, Holmes, and Volkmann. It's called B3 tree space. It's very much related, but it adds some constraints. It comes from phylogenetic trees, where you study the development of species through time. And for a phylogenetic tree, you constrain it to have a fixed set of leaves with a fixed set of labels. So in the B3 tree space, you have a predefined label space, and you only study trees whose number of leaves is the same as the number of labels, and where you have attached a label to each and every one. And you also constrain the geodesics between trees to have to identify leaves with identical labels. In the original paper, where they developed this for phylogenetic trees, they use length attributes on the edges, but everything carries over to using Euclidean edge attributes, which allows you to have shapes with the similar constraints. Now, in this case, again, you will have trees with the same topology residing in a simple space, parameterized by the edges in that particular tree. And you can think of them as living within an orthant like this, whereas changing the edge lengths moves you around. And again, if you contract an edge to 0, it brings you down to an axis. And you have a slightly different contracted topology. And again, this allows you to glue different topologies together along these edges. And if you keep doing this, you'll see that you have, for instance, structures like corners within the tree space, where you have 5 different topologies adjacent to each other. And this is the consequence of the combinatorics. Now, there is a different way of considering these trees that allows us to embed them in a Euclidean space. So because you have a fixed leaf label set, you can characterize topologically every edge in your leaf label tree through a bipartition on the label set. So by the label set, I now mean the leaf labels along with the root. Now, for instance, this edge here is completely characterized by the partition into RA on one side of the edge and BC on the other side of the edge. And you can similarly characterize all the other edges topologically using bipartitions of the leaf label set. And this will, if you take all these bipartitions together, they will define your tree for you, or the tree topology. Now, important, you cannot have any set of bipartitions like this giving you a tree. For instance, you cannot simultaneously in one tree have the edge that splits RA off from BC along with the edge that splits RC off from A and B. You cannot have these two bipartitions or edges in the same tree. So there are sets of bipartitions that don't define trees, but every tree can be defined by a set of bipartitions. So in particular, if you consider the set of all possible bipartitions of the label set, and you consider your edge attributes, whether they are lengths or Euclidean vectors, well, you can embed your BHV tree space, or you can parameterize it using the label set to the power of your bipartition set. This gives you a subset of a large Euclidean space where all the parts, or that essentially consists of, it's spanned by axes. So all the parts or all the strata in this tree space are going to consist of or be spanned by a finite set of axes in your tree space. So the figure is really quite correct. You will have a lot of trees not inside the tree, and all the parts of the tree space will be oriented along axes. You can also use this embedding into Euclidean space to give BHV tree space a metric. It's going to be path connected, it's a geodesic space when you measure the lengths within the Euclidean space. It's also singular, and the easiest singularities to see that you will have are the open book singularities and the corners. So we already looked at the corner. This is called a spider, and in fact this is the entire tree space on 3 leaves. So if you have 3 leaves, the topology can either look like this, or like this, or like this, or if you contract the branch in the middle, like this. So this parameterizes the entire tree space on 3 leaves. Now, of course, you have the only attribute that I'm actually visualizing here is the one in the middle, and then you have the additional 4 attributes that are hidden in a product with R4 here. So this really gives you an open book singularity inside your tree space. But what this means is that these singularities give us simple test spaces for things that actually happen in tree space. So if I can show that something weird happens either in a spider or an open book or in a corner, well, that same strange thing is going to happen in tree space. BHV tree space has non-positive curvature, which means we have unique geodesics. And there is also a polynomial time algorithm for computing those geodesics. So what this means, I pay a price for assuming that I can have my leaves of my trees labeled by a fixed set. And that's a big price. But what I get out is quite nice. I get computability, and I also get nice geometric properties. So this gives me a hammer or a tool, and if you have a particular tool like a hammer, well, you're bound to think that nails are nice. So looking at the problems I had with the more general tree space, where I could not compute geodesics, it's very tempting to try to bring it into this sort of a framework. So the first thing that we did was to try to use the BHV tree space metric to attach labels to these airway trees. And this is actually something that medically makes sense. These labels here are not something I cooked up. They're used in the medical literature. And then once we have an algorithm for attaching those labels, we can label a large set and do statistics on it using the more well-behaved tree space. And I mean, the idea for attaching these labels is very simple. You try to throw out a bunch of labels. You evaluate how well they fit with your training data using the distance, and you keep doing that until you have a set that you're happy with. And of course, there are voting algorithms and things that make that work. In practice, we had 3 different experts hand label our data. We had scan, follow-up scan, so we could evaluate reproducibility. And what we see is that in terms of attaching labels, well, we are as good as the experts. And this should be understood as the experts don't agree. And we are as good at agreeing with other experts, or as good as agreeing with experts as experts are at agreeing with other experts. And we are actually more reproducible than experts, which, if you think about it, is not that surprising. Humans are not algorithms. The nicest thing, perhaps, is that we did not see a significant correlation with COPD severity, except for in the reproducibility, and this we can explain with segmentation problems that we know we have in people who are sick. And if you don't have the branch, well, you're not going to label it correctly. All right, so using this, we were able to try to push our very general types of trees into the more restrictive framework. And just a little note on how these different tree spaces are related. You had the tree at a distance space, and then you had the more general unconstrained tree space with the L2 metric. So they are related via the tree at a distance boiling down to an L2 combination of edge attributes, whereas the QED it gives you an L2, or is based on an L2 combination of edge attributes. Now this relation here is more complicated. So this is how the QED tree space relates to the constrained BHV tree space. Now, if you have a geodesic in the QED metric between 2 unlabeled trees, like this one and this one, that geodesic is inherently going to match branches in one tree to branches in the other tree, like I've sort of colored here. And there are also going to be branches that are not matched to anything. And it turns out that this geodesic is necessarily going to be a product of the BHV geodesic on the matched up parts. So now I can use these colors here that are randomly generated, but I can use them as labels for my leaves. That tells me how to define the upper part of these trees as labeled trees. And so I can compute the BHV tree space geodesic between the upper part. Then I can take the product with what's left, and that is actually going to give me a geodesic in the original space. So that sort of suggests partly that the labeling idea is not completely insane, and it also suggests an algorithm for computing unlabeled geodesics by just trying a lot of different ways that you can match them up. Of course, it's still a very complex problem. Now, these tree spaces are stratified spaces. And Xavier mentioned them yesterday. A stratification is usually defined on subspace or subsets of manifolds, so that you have some ambient differential structure. So a stratification of a subset of a smooth manifold is a partition of that subset into smooth submanifolds of the ambient manifold M. And you usually ask that it satisfies local finiteness. And in the singularity theory literature, you also have various additional gluing requirements that tell you something about how these strata are supposed to be glued together. So for instance, in the tree space, you would have a stratification, or you would hope to have a stratification by tree topology. And then you can see it makes sense to envision that these are actually nicely glued together. In fact, they're glued together along linear subspaces. Now, when we represent data, I think we often want a slightly looser definition than what's used in singularity theory. I think in many cases we will have to let go of the subspace or subset of a manifold condition. BHV tree space actually satisfies all of these things, but the unlabeled tree space does not. It's not a subspace of or a subset of a smooth manifold. And quotients in general will not be. I think also some of these gluing requirements will often be too strict to represent our data. But nevertheless, I would like to keep the word stratified space because, and just use it as something that, or a set that consists of manifold parts that somehow nicely glue together. So it's a looser definition than what you'll find in literature. Now some simple examples of stratified spaces, you've seen them already. It could be the K-legged spider consisting of one-dimensional lines glued together in a single point. You could have the D-dimensional open book on a finite number of leaves. This is just half spaces glued together along the spine. Or you could have the corner singularity that we've seen, and all of these appear in tree space. So now we're going to use this to look at some of the properties that statistics in stratified spaces have, and bear in mind, everything you see is bound to happen also in tree space. So what can you do in a stratified space? Well, you have distances, you have geodesics, that's a good start. We have tangent spaces and tangent vectors. We do not have unique geodesics for each base point tangent vector pair. So I cannot, like in a manifold, I cannot say I'm going to start here and go that way and expect to do so geodesically in a unique way. And to see that, consider the corner. If I start out here, and I say, I want to head towards this corner, well, once I hit the corner, there are infinitely many ways that I can continue around the corner, and they are all geodesics. So in tree space, you cannot, in a unique way, parameterize your geodesics with starting point and direction. You can define Feragen means because we have a distance. That's nice. And under sufficiently nice conditions, you can also compute them. So in particular, in the BHV tree space, we can use Storm's algorithm that Xavier mentioned yesterday, which works whenever you have non-positive curvature. There are also starting to be some results on what happens in positive curvature. So there are some, so far it's mostly on manifolds. I think some of it might extend to when you have boundary, but let's see. But to some extent, you can certainly define means, and to some extent you can compute them. You can also define first principle components. And now this starts to be a little bit more tricky, because in the manifold you would typically say, I'm going to start in this point, and I'm going to look at all the geodesics going through it, and then I'm going to have some loss function that tells me which one I prefer. And one loss function would be the squared error that you make by using this to approximate your data. Now, in the tree space, I cannot say this is my base point and I'm going to try all the directions. So instead, I have to pick endpoints for the geodesics and look at the geodesics joining those two endpoints. It's the only way that I can uniquely parameterize geodesics is by fixing their endpoints. So instead, I'm going to be wiggling two endpoints around and trying to find geodesics between them that approximate my data as well as possible. You could also define classifiers, interpretable classifiers in tree space, again using geodesics in this way. And one way that we have done was in trying to find the geodesic segments that maximizes class separation when you project all your data onto it. And you could do this, we did it using an LDA type of measurements of class separation, but in principle you could use a generalization of support vector machines as well, any linear classifier really. And what this gives us is a linear class, or a generalization of a linear classifier that I can interpret, because then I can look at how my trees varies as I move from one class to the other. However, some of these concepts also have issues. So already with the Feragen means, they are what's called sticky. So, and you can already see this on the 3 spider. So if I have 3 trees, one on each leg of the spider, and let's say they are one away from the center point, so equal distance. Now if I start moving one of those points up and down, the mean is going to stay put. So in the case where the distance down here is 1, in fact, the mean is going to stay put until I reach 2. And it's very easy to see it. You just write out the distances, take the derivative, set it to 0, and you'll see it really has to hit 2 before the mean moves. This is called stickiness. Now, once you know you have stickiness for these spiders, well, you easily end up concluding that you'll also have stickiness for principal components. So for instance, let's take an open book with 3 leaves. Now, I'll set up a spider situation down here, and sufficiently far away, I have a 3rd point. If I start wiggling this point up and down, assuming that the distance is sufficiently long, the principal component is going to stay put. So these are very, very robust statistics. You also have other types of non-Euclidean behavior in the principal components. For instance, they do not vary continuously with the data. Oh, I don't think you can see this. Let me try to draw it. So you have this corner situation. And then you have one point up here. So this is the vertical part of the corner. And then you have one point here, and you have a last one here. And what we're going to look at is what happens when I move this point away. So assuming that this point is sufficiently close to the corner, my principal component is going to go this way, because if I start moving it like this, well, I'm going to be punishing these points without gaining anything for this one, so that's not going to happen. And if I start to move it down here, well, you can write out the costs, and that's not going to happen either. However, as I start moving this point down, I'm going to end up in one of these 3 situations. So as I move it down for a while, everything is going to stay put. But at some point, it's going to prefer to go either like this, or like this. My drawing is terrible. Or like this. Yeah. And this really depends on the values of your points. But the point is, it really stays put as this for quite a while, and then it discretely jumps to something else. And finally, the principal component also does not necessarily contain the Feragen mean. So here you have sort of the sticky setup over here, and then you have a last point over here that now you set it up so that the principal component is not sticky to the spine. So moving it a bit closer. Now in this case, your principal component is going to move above the spine, but your mean is actually going to stay put because this does not add enough mass. So you have these strange behaviors that you do not see in Euclidean spaces. As far as stickiness goes, you might ask yourself, is it the square that's the problem? And it's not. So if you try to replace the mean with a median, you'll actually see that you can move your point up as far as you want, and the median is never going to move. And the only way you're going to lose stickiness is in the limit where your power goes to infinity. So these are not just least squares problems, these are distance-based problems, if you like. And is it a problem? Well, from a modeling point of view, I've worked with these airway trees for quite a long time, and I don't see a lot of stickiness. This is a mean, and if it was a sticky mean, you would see it. It would reside in the lower dimensional stratum, and I would see that in the tree as higher order vertices. And this one could be a degree 3 vertex. Other than that, I don't really have higher order vertices in my trees, although it's actually down here that I have the most topological variation. And the same thing, this is a principal component, and again, you see there's not a lot of higher order vertices here. These might look like it, but I don't think they are. So in my data, I don't see a lot of this. And what does that mean? Well, that means I don't have a huge variation in topology. I do have variation in topology, but not enough to put me frequently in situations like these. And for a second, think about what it means to have a tree space like this. If I have geodesics from one tree to another, those geodesics inherently match branches from one tree to the other tree. So this is a model that makes sense if there is a natural matching between the trees, or the branches in one tree to branches in the other. If you don't have natural matchings of branches, well, then you are going to see more topological variability, and in this case, this might not be an optimal model. So, in my experience, stickiness was not a problem for doing statistics. It doesn't mean it never is, but maybe if it is, you should also go back and look at your data and think about this, does the model make sense? So that's what I did several years ago on tree spaces. I haven't worked on them for a while, but I'm still thinking about stratified data spaces. So I'd like to finish off by going through some other examples of stratified data spaces that I think we will see more of. The first example has been around for a while. It's a space of persistence diagrams, which you can think of as the set of birth-death times for a finite set of topological features that appear in a deformation of your data object. So they are birth-death times, as you have some data object, and you deform it through time. And as you deform it, you will have topological events. You will have topological features that are born, and then they die. So they can be, for instance, new loops in your data, or something like this. And because they are birth-death events, well, all the points will be above the diagonal, and each data object will be represented by a single diagram like this. So it consists of finitely many birth-death pairs, and countably many copies of the diagonal that you can use to match up with birth-death pairs in a different diagram if you don't have the same number, or if they don't match. So here you can stratify your space of persistence diagrams by the number of birth-death pairs, or of diagonal points if you like. This is actually closely related to the tree space where you have only a single generation. So here too you have to match points up. Here the points are not branches, they are off diagonal points, but they are matched up in an unordered way, or in an unconstrained way, and if there's nothing to match it with, well, then you take it away by moving it to the diagonal. In this case, there are actually analytical formulas, I believe, for geodesics and means. So here, you can actually do some statistics. You can also study spaces of graphs. And this has actually been around for a while. So Pranesh Jain, back in 2009, had a paper where he defined a graph space. He called them structure spaces, but one instant of it is graph spaces, defined as a quotient of the space of symmetric weighted adjacency matrices on n nodes. So if you have a graph that's less than n nodes, you just pad the adjacency matrix with 0, so you reach n nodes. And also in this case, he did not have a labeling or a matching of the nodes, so he used the permutation group to match up groups by factoring out the reordering group. And although he doesn't phrase it as such, but he also has a stratified set, where you have stratification by graph topology. His computational tools were Lipschitz optimization, which might be something we should also look into for more general stratified spaces. But he was able to prove all kinds of statistical properties for graph spaces. One of the things that is maybe different here from what I have in the tree spaces is in the adjacency matrix, when a branch goes to 0, it's not contracted, it disappears, and you get the disconnected graph. So this gives you a different model. And I've talked to him quite a bit on how you could make a model that had both, and we still don't know how to do that. Some simpler stratified data spaces that you know very well, manifolds with boundaries, such as a symmetric positive semi-definite matrices, are one example. Or group quotients, such as Kendall-shaped spaces, are a different example. And of course, these are spaces that we're familiar with and we're used to working with them, but very often what people do is they assume you avoid the singularities and then off we go. And you can do that. But I don't think there's any reason to. I think we can handle those with tools we have. And finally, recently there was proposed a different type of tree space, which is somewhat similar to what I had, but it's constrained to trees that have a main branch and side branches. I think the blue one is the main branch, actually. Which again means you're essentially looking at a generation 1 type of phenomenon and you're trying to match up the branches. So it's actually, again, related to trees of generation 1 or persistence diagrams. And they were using elastic metrics on these, so they get slightly different type of metric, but it's still a stratified space. And you get a stratification by the number of branches. So in summary, stratified spaces extend manifolds. And we do have quite a few tools that carry over. Some of them have some unexpected behavior, but in fact I say unexpected with quotation marks, because once you see it and you start thinking about it, maybe you should have expected it. So the pros of this, I'd say, is, well, the classical approach to handling singularities is to pretend they aren't there, and I don't think we need to do that. And the other pro is that we're modeling the data in their own domain, which means the stratification in particular is very useful for explicitly modeling structural variation in data and gluing structural differences together in an almost continuous way. And finally, this gives us a way of building interpretable tools. Now, as cons, I'd say the most important one, at least my experience from working with trees, is that you actually have to think about what your model means. So geodesic models implies a local matching of your objects. And this is not always a good modeling choice. And in my experience, this is what often brings you into sticky situations. So one of the things we're currently looking at is whether we can also represent trees not as global objects, but rather as products of a branching process. And can you maybe do statistics on trees via doing statistics on the generating branching processes instead? Of course, that would not give you a stratified space, most likely. But for some types of trees, I think that might be a better model. Finally, for the unordered trees, I ran into computational problems. That's not something that is inherent in stratified spaces. It's inherent for hierarchical structure. So I would not expect this to be a general problem. Just not to scare you. All right, thank you.
Questions?
Okay, thank you for this very nice talk. Something I would like to understand when you're modeling preliminary trees, in a sense, in any of your models, do you have a way to take into account the proximity of the branches? I mean, if you have two branches and okay, they are closer or not.
So do you mean in the same tree, or you mean in different
the same
trees?
trees? You know, you have two branches like this, but you change their proximity in the space. So the positioning in the ambient space.
I see. The way we typically encode them is, well, the proximity in space, or the translation, if you like, is captured by the position of the root. So you put the root somewhere, and either you try to align them so they are the same, or you don't. So the position of the root will give you a position in space, and all the branch shape or geometric information that we put, we actually encode as being relative to the root. And one of the advantages is that well, if you don't have a branch, then it's really zero.
Yeah, I was thinking about the fact that when you have two branches, so you have a point and two branches, but now they are the same shape, but they position, relative position in the 3D space is changing. And so, do you have in this formulation, do you have a way to take this into account, or?
Sure.
Yeah,
so that's captured by the length of this branch.
No. See, okay. But this is, in fact, I think this is something about the coral,
or a V-shape, like
evolution of, yeah. Yes, you, okay.
So you're saying, can I measure how different those shapes are?
They move away from each other.
Ah, like that? Well, so I've usually represented the branch shapes with landmark points. It's a very simple model, but it does capture like the shape on some level. You could also use...
Okay, so you have a way to position, okay, because you have a shape, but you have to say how you put that shape in 3D space. So that's what's confusing me in a sense. But okay, maybe we can discuss.
So I'm not representing them as shape. I'm representing them as spatial coordinates. Okay. So the position in space is there. I think what's not there is modding out on a branch basis, the orientation and scale, etc. I'm not doing that, which is also why I tried very hard not to call them shapes. But sometimes I slip.
For graph, classically people use Laplacian matrix to describe graphs. So could we extend metric space with Laplacian matrix or Kirchhoff matrix for graph? Probably.
It's just a constraint, right? So I think so.
I don't know if it's applicable for trees, but...
So the reason why I'm not representing the trees using adjacency matrices is that in the graph space where they are represented using adjacency matrices, usually in the adjacency matrix, a 0 in weight usually means there's no branch. So for instance, if I gave this edge here a 0 weight, I would get a disconnected graph. And for the trees, I don't want that. For the trees, I want the zeros to mean contraction of the branch. I want that to mean that they are somehow connected. And in order to get that, I need the hierarchical structure in my structural representation. And in an adjacency matrix, I think that would be hard to encode. I think you can do it, but it would mean a lot of constraints on the adjacency matrix. And I chose not to do it because it seemed complicated.
Yeah, so you had the first principal component that you described. Can you get further ones, like the second, third, fourth principal components, or is it just one that you have?
For now, it's just the one. So we are playing around with all kinds of ways of doing the second, etc., and we're definitely not finished with that discussion.
No.
And it's because if you try to look at the portion of tree space spanned by, let's say, 2 initial vectors, that's not necessarily going to get you a 2-dimensional subspace. In fact, it could get you a really, really large space. And we don't know, for one thing, we don't really know what is the correct subspace. In fact, I'm not even sure we agree that geodesics are the right 1-dimensional approximations, because you could have things splitting up that we cannot represent in this way. So moving to 2D is hard. Also because in Euclidean space or even on a manifold, you can project onto the orthogonal complement. But what does that mean in the tree space? What is the orthogonal complement? Even that is hard to say. So we cannot even project onto the orthogonal complement and repeat the procedure because we don't know what that means.
Okay. But couldn't you just say for all the points on your principal component, then just find other geodesics which pass through that? That
is one of the things we've tried to do, and they look really strange.
Oh, right. Okay.
So I think the closest we have at the moment is Savier's barycentric coordinates.
Yeah.
They would define both branching subspaces and higher dimensional subspaces.
Thanks.
Yeah, I guess actually just to complement, if we're starting with different tangent vectors, as soon as you're taking different points, not the original points, but geodesic between other points, you're generating a higher dimensional space. So actually the convex hull is generally larger.
Yes.
You have to be geodesically complete at all the points of the subspace if you want to have some good definition. So I think somehow it's bound to fail if we go that direction.
Yes. So there are some really non-intuitive things happening.
Yeah, you did not say much about the combinatorial aspect of the trees.
No, I did not.
And said you were optimistic on the computation. So basically, can you say a bit more on those aspects?
So are you talking about the combinatorial aspect of B3 space or of the... Yeah, so there are the different types of tree spaces, and the one where we have computational tools at the moment, that is the B3 space. And those computational tools, they rely very heavily on the combinatorics of the edges. So most of the arguments and most of the things that go into it are combinatorial arguments, and the combinatorics is very important. The problem is when we move into spaces where we don't have a fixed set of leaf labels or even a fixed set of leaves, we don't know what to do combinatorics on. So the closest we are to that at the moment is by linking this tree space to the B3 tree space. And I think that might work, but I still have to, I know that as long as I have, as long as my trees are not ordered, I know for a fact that computing geodesics is NP-complete. So, and that is because even though I have this link, I have to look at an exponential number of different ways that I could use that link and pick the best one. So it's pretty pessimistic, really.
Okay, maybe a last question on the stickiness.
Yes.
So one of the, well, it seems to me in your case you have principally negative curvature, at least at the corner here.
You mean up here?
Where there is stickiness. Yeah.
Yes.
And so in the case of quotient spaces that we have looked at recently, we have a positive bias, which is we have a positive curvature, and then it's the bias is getting off from the singularity. But here with negative curvature, it seems that it's the opposite. There is an attractive bias, and I don't know. I mean, do you think there could be a relationship with curvature or feeling the curvature in some kind of well, with the distribution? I don't know if you have seen the experiment of Tom Nye. He did some random walk on the space,
yeah,
and then with the generative model, he tried to find what is the the maximum likelihood. Actually, the maximum likelihood is not sticky.
No, it's not.
And so it seems that there is something that may be common, although we're talking about, well, I'm mostly talking about something which is continuous version, and here we have the singular version of that.
Yeah, so the question for me is whether it's about curvature or whether it's about having multiple sheets. I mean, I guess the experiment we should be doing is look at manifolds that are approaching something like the spider in structure, and see whether we start to see stickiness before it really hits. Because I don't know. Well, maybe that means it is curvature, but
well, maybe there are several effects. So
yeah. So another thing that I don't know is what happens when you have unbounded curvature from above. What happens then?
Okay, so that's a good work plan.
Yes.
Okay, so let's thank Aasa again.